Welcome. This is another AQAA2 physics etc. video. This continues with our electric field topic, or chapter 5 in your AQA book. Again, just reference if you're using your AQA book like I produced in the last video. I'll be starting now on 5.2. This is called electric field strength. Now you don't need to worry if you don't have the book, because I'll be going through the vast majority of it on here anyway. Anyway, so let's get started. So I'm going to do it slightly differently to how I've done it in recent videos. I'm just going to sort of do a mind map for this video. So electric field strength. And now the reason for this is because I don't think this section, or what this video is going to be about anyway, is requires too much writing down. It's mainly talking you through it essentially. So electric field strength. So I'll just put in 5.2 for the people who have the book, as it said. Okay, so electric field strength. Now the first thing we're going to do is we're going to essentially define electric field strength. What is electric field strength? Well, electric field strength in words, and see if you can try and formulate the equation from this, so this gets you thinking about it. The electric field strength is defined as the electrical, oh no, I won't put that in that confusion, the force per unit charge. Strictly speaking, it's the electrical force per unit charge, but just because when you formulate an equation it might confuse you if you put electrical force per unit charge. Okay, so if you drive that equation, it should be the electric field strength, I'll just put denoted by E, equals the force per unit charge as over total charge. And obviously you could use your old AS physics equation for Q. I think Q equals IR was the main one that people used, if that's the right way around. So E equals F over Q. So that's the electrical force per unit charge. So that's what electrical field strength is. Now the reason I'm not going to go into too much detail about it, there is a worked example on here, which again I'll go through for the benefit of you who don't have the book. So I'll just put like a little, oh god, some static build up there. So anyway, electrical field. So we're going to be using this equation essentially, so you need to keep your mind on that one. Sorry, actually the example in there is not brilliant. Okay, well we'll use this one. So obviously you should know your charge of the electron. So electron charge. You should know, this just says it in the summary question. This is a summary question 5.2, question 1A. Oh, actually, you know what, sack it. I won't do the summary question, just change the mind. It's pretty pointless, I need to talk you through it first. I'll do some quick chapters. I just thought I might as well do a summary question now, but sack it. So hopefully you've understood that the electrical field strength is the force per unit charge, or force over total charge. Now what you may see, sometime, hopefully you will see, is your when the lightning strikes hit the ground, and how does it actually, what's that actually showing us? It's not just a magic light coming from the sky somewhere and hitting the ground. Well, obviously you know how it goes through when it hits something metal, but how does it get from the air, from where it originates to the metal pole or whatever conductor you may have? Obviously, if you're not sure what a conductor is, look at our previous electricity video, chapter 5.1. It should be the video before this in the playlist if I get my computer to actually be bothered to upload something for once. We should make a change. Anyway, so basically in the air what we have is the clouds that build up charge. So I don't need to go into too much detail about that. So basically clouds build up charge. It doesn't in this book, so I'm assuming you don't need to know this so much. Clouds build up charge. And obviously, well, it's not so obvious, but the air molecules are sort of insulators up to a certain point. There's no name for that point, what it builds up to, but I'd like to come up with one, but I'm not going to confuse you by saying one. So basically, they build up charge, and then the air is an insulator until a certain point. And then when this charge gets past a certain point, so when the charge reaches a given point, or reaches a certain point, it overcomes the insulating effect of the air molecules. Sorry. I'm trying to write as fast as I can, but it overcomes the insulating effect of the air molecules, and this causes just a discharge. Tried to make something reference there, but never mind. The air molecules, it releases discharge of electrical energy, and obviously this electrical energy goes through the atoms in the air, as you should know. Air is just made up of atoms, as such as everything is. So discharge of electrical energy. And this then ionises. So that's testing your AS understanding. So ionises the atoms in the air molecules. So you should remember, ionises is where a electron is taken away or added to an atom, and obviously in this case it's taking it away. So the ionises the atoms in the air molecules. I obviously think you should know they're taken away. I don't need to write this down. Ionises the atoms in the air molecules, and this sort of continues, and that's what gives off the bright sort of light. So and obviously then this reaches the floor, or reaches a conductor, and passes through. Due to, obviously if it's a conductor, it's what we spoke about in the last video, passes through the free electrons in the metal. And we said free electrons aren't attached to an atom, which obviously you should know if you took GCSE chemistry, but just a quick reminder there. And obviously ionises is, again, something that we did in AS physics, which hopefully you should be familiar with in terms of particle. I don't think I did a video on it, but I did a DVD, just didn't upload it because I'm lazy. Okay, so that's the build-up of charge. That's how we see our lightning strikes coming down to Earth. So hopefully that explains, and it's just a bit of interesting background knowledge really. As I said, the main sort of physics bit of this that you need to know is the electrical field strength, which is the force per unit charge. Another thing that you will get asked, so well, basically another way of saying this, so it might not always be saying, oh, something as easy as saying rearrange that equation to get Q, and it will give you some values for the electrical field strength and a force. It could be something a bit more complicated. So, for example, we could have two parallel plates. So if I draw a battery here with the given potential difference V, I'm going to call it anything, just to make it simple. I'm going to call positive, negative, and obviously this is going from positive to negative, as you should know. So we've got a positive plate here with all the positives, and a negative plate there with all the negatives. I'll move out the way in a second. So I'll just see if you can still see that. And then what we've got there is all the positives, all the moving across like this, positive to negative. And we'll call this distance between these two plates, we'll call it D. Okay, and we've got positive, negative here, we've got potential difference. So how can we make some kind of use from that? Okay, so if we remember our old equation, so this equation, what we're going to do essentially to this is we're going to modify this equation so we can use it in the context of this. Okay, so just to put your mind back into that equation, so we're going to start from this equation. So what we'd want is the force, okay? So we're going to rearrange it to get the force. And we don't need to worry about this just yet. Just rearrange it to get the force. So the force is equal to the electrical field strength times the charge, okay? Now there's a distance here. Now the electrons are moving across this distance, and when we move across a distance, what we do is we do some work done. We produce results essentially. And if you should remember, work done is your force times your distance. And we've got the force here because we rearranged this equation to get the force. So we sub in F there, okay? And if I'm right, well, it should be right. We get D, and then obviously we rearrange it, we get D is equal to Q, the charge, times E, the electrical field strength, times your distance. What? Oh, sorry, no, for goodness sake. I was reading it wrong. I thought it was wrong. So force times distance, so it's your force, and then that's your work done. Sorry, because on the book, I was reading from the book to make sure I get it right, and it's got the D, and it looks like it's part of this equation, but it's just the letter they've given said this is what the distance is. Okay, so obviously it's just, that's the work done, because all we've done is substitute F into that, and left the D in there. Oh yes. So anyway, hopefully that sort of helped you a little bit. But say if we wanted to work out the electrical field strength from this equation, and what we'd want here is we want that A there. So what other equations do we know for electricity? Well, you know that includes the work done, force, work done, potential difference, because we've got potential difference, and charge. Well, you should know, W equals QV. Well, or VQ, or whatever you want to call it. Okay, so obviously this allows us to get V is equal to W over Q. Or we could have Q equals W over V. But we've got work done here. So we want something with W on top, and we don't know the charge because it's here. So what we can do is you just sub in this one, because we've got work done on top, and we already know what work done is. We could use this one, but for my demonstration's sake, we're going to put in V equals W over Q. So we've got this W, so we don't need to write W, we just need to write V is equal to Q, electrical field strength times the distance between the two plates, over charge. And then obviously the two Q's cancel out here, so what we're left with is the potential difference equals the electrical field strength times D, and we can rearrange this if we wanted to get E, or the electrical field strength, it's V over D. So these two equations here, so that one and our good old friend, this one at the bottom, mean exactly the same thing. But this equation here is relevant to that, what we just done there. Hopefully that makes some kind of sense. I don't know if you saw all my hand movements on the board there. Yeah, I did it a little bit too high. So basically what we're saying is that equation at the top, which is sort of the equation of the definition of electrical field strength, this is a force per unit charge. Is the same as writing that there at the bottom, which is the electrical energy, which is the potential difference over the distance between their two parallel plates, which is you're more likely. And the reason we did all that working out there was because there's certain things in our method there that actually gives us set equations. So the work done, for example, you might be asked the work done in a situation like that, and instead of, we couldn't really use E equals F, the force over the charge, for that to work out the work done. So we might be asked to use that equation, which is just the derivative of the first equation, and all we've done to get that equation at the bottom there equals V over D. All we've done is we've rearranged the top equation and subbed in one or two equations that we should know from AS topic. This is sort of a proof that this is a synoptic topic. So basically what we've done is we've adapted our AS knowledge, put it in the context of rearranging a A2 equation that we're given, and sort of come up with a new idea. Okay, so hopefully that's explained a little bit, and hopefully you shouldn't really, and you might not be able to work out that so well as you first go, but as I said, the bit on the left when we talked about the electrical energy coming from the lightning strikes and thunderstorms. That was just a bit of background knowledge. It's more the right hand side of the board that you need to worry about in terms of actually answering physics problems that you may get given in the exam. One thing I'll just stress at this stage, which I'm assuming you should know by now if you're watching this towards the end, just for information. The AS topic was, we just did a couple of written exams, and then I said, whereas the A2, what we do is we still do the ISA, and we do a multiple choice and a written paper, so it's slightly different. But anyway, it's just a quick overview. I think I should have mentioned that in my first video, but if I didn't, I'll mention it now. Anyway, so just as I go over this again, we just said the electrical field strength is the force per unit charge, so that's force over total charge. It's just breaking it down per charge, but essentially is what it's doing. And then to get the, as you can see, the sort of towards the bottom of that right hand side there, we talked about the two parallel plates, and what we did to get that equation for the electrical field strength of that given situation is we used the original field strength equation, which is the force over the divided by the total charge, and we rearranged that to get F, which obviously is dE times the total charge. We put in our other equations from what we should know from AS topics, and then we sort of rearranged that to get our final E equals V over D. Or E, the electrical field strength is the potential difference over the distance between the two plates. And just another thing as well, I didn't mention it, but I probably should have done. Between them two plates, it's the electrical field strength is something we call uniform. Now, I think I did mention this in the gravitational videos, but if I didn't, basically uniform field strength is the same as uniform electrical field strength, because they're both fields and they're both uniform, so they're the same all over. So hopefully, again, so that makes some kind of sense to you. But anyway, as I said, that's been a start of 5.2. In our next video, we'll be looking at the electrical potential and going back to our favourite equipotentials, and sort of applying it not just, so we've sort of got our knowledge of the equipotentials, but we're talking about electric potential instead of gravitational potential in that sense. And then we'll go on Coulomb's law, point charges, and comparison between gravitational and electric fields, which is sort of just a combination of the two previous chapters. And then that'll be electrical field strengths done, and we'll be going into electromagnetic induction, capacitors, etc. And that'll be the end of Unit 4. So not that long to go now of Unit 4. As I said, hopefully that's been watchable, and we'll see you in the next video.